ready? I guess we're not waiting for Sarah, so. Are we good? Because Sarah's not going to come until later? Yeah. All right. Okay, welcome everyone to our Nanoscience Lab A Summer 2024 final presentations here at the California Nanosystems Institute at UCLA. My name is Dr. Shailene Tanimoto, and I'm the Education Manager here at CNSI, and I've had the privilege of being with your students for the last week, and we're really excited to show you all that they've learned this week. So I'd first like to start by welcoming everybody to UCLA. UCLA was founded in 1919, and we are the second oldest UC in the UC system. Our campus spans 419 acres, so it is a huge campus, and we offer 337 undergraduate and graduate degree programs. We have 31,600 undergraduates here on campus, 10% are international students, 31% are first-generation students, and 42% of those undergraduates are in the life sciences and physical sciences. And so we're here today at the California Nanosystems Institute, and so CNSI is one of Governor Gray Davis's Institutes for Science Innovation located here at UCLA. We were originally established in 2001 as an engine for innovation based on the belief that the defining technologies of the 21st century will arise from understanding and constructing functional nanosystems through controlled integration of nanoscale components. So our mission here is to be a world-leading nexus of research, education, and translational activities by engaging in scientific discovery that fuels innovation and impacts society. And so why are we interested in nanoscience, and how small is nano? And so nanoscience, the definition, is the study of things on the nanoscale. Okay, so this is 10 to the minus 9 meters. And these are things that are really, really small. So to help you visualize how small this is, we want you to think about a virus particle. This is a nano object. These are about 28 to 30 nanometers in diameter. And if you think about the number of virus particles that can fit on the surface of a standard size football, you know, like you sneeze on your hand and then you grab a football and throw it, how many virus particles would you put on there? That is equivalent to the number of footballs that could cover the surface of the Earth. Okay? So nano is really, really, really small. That's like over 1 trillion particles that would fit on the surface of a football. And what we love this length scale is because it's an interdisciplinary field. And so interesting physics and chemistry happens at the nanoscale, and this has far-ranging impacts in a variety of fields like chemistry, physics, biology, material science, and medicine. And so your students had the opportunity to learn about a variety of these topics throughout this week. And so here at CNSI, and our education team is led by our faculty director, Professor Sarah Tolbert. She will be joining us later. She is a very busy lady, and so she'll be joining us later, and you'll hear from her in a bit because she will want to address the challenging program that your students have been through this week. And so our education outreach programs include K-12 teacher training workshops in nanoscience experiments. So the same experiments that your students performed this week, we teach those to teachers, and we provide them free kits of materials so they can take that experiment back to their classrooms and teach their students. That is what we do mostly through the academic year. We also have a Nanovation competition for 6th through 12th graders that combines nanoscience and entrepreneurship. We host public outreach demos, and then what you're all here for today are our summer session programs for high school students. So our class this week was Nanoscience Lab, and we have many learning objectives for your students. So our learning objectives for skills in science have to do with nanoscience. So, you know, what is nanoscience? How small is it? Why is it interesting? How does it appear in our everyday lives? And we wanted them to learn about being a scientist. So what does it mean to be a scientist? How do scientists perform experiments? And what tools do scientists, particularly nanoscientists, use? But, you know, not all of your students may go on to pursue a career in science. And so we also wanted to have skills in life for them. So these will translate beyond the science disciplines. And so this includes a growth mindset. This is really important. So this is the belief a person has that they can learn more or be good at anything if they work hard and persevere. And your students this week, they worked really hard and they persevered through a lot of challenging prompts and activities that we had for them. Other skills in life are critical thinking, communication, collaboration, teamwork, empathy, creativity, curiosity, problem solving, and reflection and introspection. Yesterday, I had your students write little post-it notes about which of these skills in life they employed in this last week. And they wrote them on little post-it notes, and we posted them up in the lobby so you can take a look and see how they used some of these skills earlier this week. So this Nanoscience Lab is a one-week summer program for rising sophomore and graduating senior high school students from around the world. This session, we had 34 students enrolled in our college-level science program. And your students had the privilege to learn from a team of UCLA STEM undergraduates, graduates, staff, postdocs, and professors. And they received state-of-the-art tours of some of our amazing facilities here. And so in the morning, your students performed a nanoscience experiment. And in the afternoon, they heard from a variety of guest lecturers. And then we had some science-themed afternoon activities that related to the experiment they performed in the morning. And so I have been trying to be better about taking pictures. And so I took some pictures throughout this week. So you'll see they got to don on some lab coats, and they worked in groups to perform some experiments here in our lobby. They also had the opportunity to hear from some amazing UCLA professors, Professor Ben Schwartz, Professor Jose Rodriguez, Professor Ann Andrews, and Elizabeth Arnheim, a graduate student in the Dino DiCarlo lab. And we had some amazing science-themed afternoon activities. Some involved guest lectures, some involved performing additional experiments. Students got to test some solar cells, and they also got to go to Young Hall, our chemistry department, to perform some UV vis experiments. And so, as you can tell, they did a lot this week, and there were a lot of people involved in making this happen. So we just want to give some thank yous right at the top to all of these amazing people that contributed to helping this program happen. So we have a special thank you to all of our instructors. These are UCLA graduate students in various STEM departments here. We had 21 volunteers help us throughout this week. So just give a shout out to some of them are here today, but we want to give a big thank you to them. Next, I'd like to thank our resident assistants, Kylie and Emma. They just graduated this past spring, class of 2024, from the chemistry department here at UCLA. They were living with 18 of our students up in the dorms, so they lived with 18 high school kids for 5 days. I do not envy them, and we are very grateful for them. Okay, and then we had our amazing guest lecturers, Professor Jose Rodriguez, Professor Ben Schwartz, Professor Ann Andrews, and Alyssa Arnheim from the Dino DiCarlo lab. All of them gave great lectures related to the experiments that your students did, but they also told your students about their journey from high school to where they are now, and the process, the thought processes, the decisions that were made along the way, to hopefully give your students some context on how they might navigate their future. So thank you to our guest lecturers. I'd also like to recognize some volunteers that helped us develop some new afternoon activities for our students. So it's been about 8 years since we've done this solar cell experiment for this class, so we had to develop some new afternoon activities that included testing various solar cells. So your students made dye-sensitized solar cells, but they were also able to test silicone and SIGS solar cells developed by Diego and Alex, and then improved by David and Susan. And then Narayan gave an amazing guest lecture. He is from the Institute of Environment and Sustainability. So he talked to your students about solar energy, the economics, and the policy involved. So tying our science research that we do to society. And then on Wednesday, we had our biosensors lab, and we've never done that lab for this class. So we really had to develop some new activities for this. And so Randy, Andrew, and Diana helped us develop this water splitting experiment. So using various catalysts to help us split water into hydrogen and oxygen gas. And then Justin Bossenbrook from the Otham Valley lab gave us a talk on biological catalysis, which is what their lab does. So I just wanted to thank these people. They put in a lot of time and effort into developing new activities that we rolled out this year. Okay, and last but not least, we have our Technology Center staff and CNSI staff who helped give our students tours of the amazing facilities that we have here. So they got to see an electron microscope in use. They got to put on some bunny suits and go into our clean rooms. They also got to see our nanopico characterization lab and our advanced light microscopy and spectroscopy lab. And then our events manager and our work study students, they helped arrange lunches for us every day. So that's why we had food, was because of these amazing people. And then our digital communications manager, Mark, is back in the booth making our live stream happen right now. And this is why the screen is on and my microphone works. So thank you all for helping make this happen. Okay, so now it's time for the main event. So the goals of this class was to expose your students to some advanced topics in nanoscience, some really cutting edge research that's happening right now. But it's also to help them develop life skills, and specifically skills in communication. And so for homework every day this week, your students were tasked with this really crazy thing that we ask them to do, where they have to draw a picture, analogy, that explains the essence of a nanoscience concept without literally drawing what they did. So the idea of this picture is that you can show it to someone who has no scientific background or context, and they could understand the science context just from the picture that you drew. It's crazy, is a crazy thing. Sounds crazy, it is crazy, and they did it, and they've been amazing at it. We will be featuring artwork from students that drew pictures this week and turned it in for homework. And then we've assigned that picture to a different set of students, and they're gonna talk about that picture. So they were not allowed to ask the artist what they were intending to show. Your students have to just interpret the picture, use their science knowledge, and then tell you what it's about. So they will present on their picture for 5 minutes, and then we will have 5 minutes of questions from the audience. So, I'm looking at you, audience. You need to be very good participants. And again, the idea of this is that these images are meant to be understandable to people who are not familiar with the experiment or the science. So, any question is a good question, okay? You don't need any science knowledge to ask a question. You are also allowed to ask your students what else they did that day. You know, like, what did they learn? What did they take away from it? So this is your chance to ask any questions you have, and I will stare at you and sit in silence until I get volunteer participation. So if you don't like awkward, uncomfortable silence, then just participate. It's easy. Okay, so we're gonna have the first group, the first 6 groups present, then we'll take a 15-minute break, and then we'll resume with the final 5 groups. Okay, so you all know your group numbers and your order, right? Okay, so we'll have group 1 come up. While they're coming up, I will remind you about our microphone usage. We like to be pop stars. We do not want to hold the microphone like an ice cream cone. We are pop stars. So when your head turns, the microphone moves with you. Because if your head turns and your microphone doesn't move, then nobody can hear you. Okay? So we are all pop stars. Channel your inner Taylor Swift. Okay, they're on green. Green. Okay, and then if you want the laser pointer as well. All right.
Yeah.
Hi, sorry. Is this working? Yeah, hi, my name is Kayla Shin. I'm from North Hollywood High School. I live in North Hollywood, and I'm a rising senior.
Hi everyone, I'm Adam and I'm from Taiwan and I'm also a rising senior.
Hi everyone, I'm Nathan and I'm from the Bay Area and I go to Piedmont High School. I'm a rising junior.
Okay, so first we're gonna talk about what we actually literally see in this image. What we see is a thrift store and a cashier. The next scene is person 1 turning in some cash and person 2 turning in some clothes. And in the next scene, we see person 3 and person 4 both turning in some clothes. And in the next scene, they both walk away with money. The next one is this man puts his hand into a box of mystery, and he touches something inside, and then he thinks it's a shoe.
And then the last one is there's a fingertip toppling over a domino.
Okay. We think the first scene with person 1 and person 2 is deconstructive interference because, or we think it's deconstructive interference because person 1 is turning in money to the cashier who's going to then pay person 2 money for the shirt or the shirts that person 2 is selling. And then in the next scene with person 3 and person 4, we think this is constructive interference because they are both paying the cashier money and the cashier is paying or giving back the, oh wait, no, never mind. Person 3 and person 4 are giving are selling their shirts to the cashier who's then paying person 3 and person 4 money for the shirts. And both person 3 and person 4 walk back with money. And then we think in the next scene with the box of mystery, we think that is indirect measurement because instead of seeing a shoe, the person is feeling the shoe. And we think that's a way of indirect measurement because the person is like making contact with the shoe with their hands and not their eyes. And we think in the last scene with the dominoes, we think the finger at the very corner is an atomic force microscope because it's similar to the point where it's touching, like the tip of the finger is touching the bottom microphone, or what am I saying? The bottom domino. The bottom domino. And we also think that this is how changes on the nanoscale can affect changes on a human scale because the smallest domino is then going to make change and knock the bigger dominoes to then affect the biggest domino. So yeah.
Then I'm gonna talk about some limitations of this picture. So first of all, we're a bit confused about what is that $10 sign on the cashier. Because on the bottom right corner, that thing becomes $6 sign on the cashier, but it says 10 minus 6, so it should be 4. So we're kind of not sure about what that thing represents. Yeah, and for the indirect measurement, it put their hand into the mystery box and thinks that's a sneaker or shoes, but like technically that is indirect guessing, not like indirect measurement. Indirect measurement should be something that is more of a numerical result. Yeah, I think that's also the limitation, because like overall, I think this is a pretty cool picture. I mean, I'm not a good artist, so I mean, this looks cool to me. Yeah.
Okay, so I have first a comment and then a question. Also, hi everyone. My name is Rita Blake. I'm the Director of Education for the CNSI, so nice to meet all of you. No need for applause, but thank you. First, a comment which is just like for all of the teams. When you're talking about the limitations of the drawings, just to clarify, all analogies will have limitations at some point because it's not literally the experiment. So I would avoid using any phrasing that sounds like a critique against a drawing, because there is no analogy that is a perfect analogy. But that being said, I would actually ask if, for the box of mystery, you were saying it's an indirect measurement. And it could be that, but I actually think that that is one of the techniques that you guys did this week. And I think you already mentioned this technique, but if you're thinking that that is describing that technique, can you elaborate on then how that technique functions and how this relates to it?
Well, we are thinking of that might also be the AFM because of the fingertip thing, but like, but normally when we want to see the thing in a box, maybe we can just peek inside the box, just like what that person was originally doing. But obviously he cannot see through that small hole, so he tried to use some more indirect way of feeling what's inside the box by feeling the shape of the shoes and like make an educated guess about the object in the box.
Great, thanks.
Other questions?
I'm kind of confused about what you mean by direct versus indirect measurement. I mean, I kind of look at it like if I'm seeing something, right, it's really just photons between the object and my eyes, and then you got the additional layer of the photons being interpreted inside your brain, versus if you're touching it, you've got these nerve impulses from your hand direct to your brain. Like, what? I'm just kind of confused as to what you mean by direct versus indirect.
Okay, great, thank you. What I meant by direct and indirect measurement is that direct measurement is by using a ruler to measure something in a numerical way, and indirect measurement will be calculating or comparing things to the things that are already known with a known value. So such as using Pythagorean theorem to find the hypotenuse of a triangle. That's kind of like indirect measurement. For example, 3 and 4, then that hypotenuse should be 5.
Can you guys tell us what the experiment or the application for picture number 3 was, what you did in the lab, or what your project was in relation to that picture?
Oh, well, actually, for number 3, in case of the AFM, we didn't actually get to like mechanically use an AFM, because I think you need like more experience like teaching before you actually get to use the machine. But we got to like see it and like on the computer, like the results of like what it actually looks like. But yeah.
Could you describe what an AFM is?
It's like a machine where there's like a nano like tip, and that tip gets to like touch or like kind of scan slightly above like the surface of an object, and then as slowly as it scans, it shows on the side of a computer like what it looks like, super zoomed in.
Any last questions? All right, thank you guys. Okay, group 2. Oh, wait. Who is our artist? Laura. Okay, say your name, and is there anything else that they didn't talk about here that you wanted to show?
Well, hello everyone. My name is Laura Marques Campora. I think that they covered mostly everything. The first part they explained quite well. I even like that they put two concepts in the second part that I had just thought about one. The only thing is the thing of the 10 minus 6. I'm feeling like I'd better explain this because I just feel like it looks like I'm dumb, but I'm not, guys. It's just because the idea is that if each shirt is worth $1, then they give in 4 shirts, and he now has $6. So he gave in $4, but he doesn't know how much he has. So he does indirect measurement, doing 10 minus how much he has now, and then it is 2 times 2 shirts. But the rest, I think they interpreted everything so nicely. So congrats, really.
Okay, great. Thank you. Okay, now group 2.
Okay, good afternoon, everyone. This is Lena from South Korea.
This is Yi from LA.
This is Daniel from Arcadia.
Okay, so we're gonna start with an interesting information. Did you guys know that an area of 150 kilometers squared of solar panels can actually power up the whole country of the United States? So that is basically what solar panels do. So they convert the sunlight into electricity into the form that we can use.
So we made solar cells, or our own dye-sensitized solar cells using dye, which acts as an absorbent of light, TiO2, which acts as a nanoporous material that houses the dye and facilitates the transport of electrons, iodine, which acts as the supplier of electrons for the dye, sunlight, which excites the electrons on the dye, and finally the electrodes that bring it all together by conducting electricity generated from the excitation of electrons.
Okay, so what does all that do with this analogy? So let's start with the things that we can literally see.
Yeah, there's a sign on the top said theme park 24/7, and the bus are taking people to the roller coaster, and they line up and wait for playing. The cars full of people are running on the track, and there's an exit which people wait for getting on the bus, and the bus take people away.
Okay, so what we first thought when we saw this analogy is that the people would be the electrons. So the electrons then go on to, so the theme park, so we thought would be the light that excites the electrons at first. So they come to the theme park, which is the light, which attracts the people. And then the people get on the roller coaster, and we thought the roller coaster could be the dye because people get in the roller coaster and get excited. So the electrons in the roller coaster is excited right now. And then the track would be TiO2. So the electrons in the dye is carried on the TiO2. So it transports the excited electrons in the dye to the electrode, which we thought would be the exits there. It comes into the exit and then goes out. So we thought it would conduct electricity because it lets the electrons flow. And then the bus would be the iodine because it constantly supplies the electrons into the dye. And then this whole thing is about how the solar cells work. And we thought it also conveys another idea about solar cells. So it says 24/7 theme park, and we thought the theme park would be the light. So light is not 24/7, but what we thought is that the track has the shape of a lemniscate, is it right? So it's like an infinity shape. So we thought that symbolizes that solar cells actually have renewable power and renewable energy that we can use constantly if we have electrons coming in from the bus and the light, which it says is 24/7.
And try the new ride for free and earn a coupon are the two signs that represent the government subsidy. The government let you try the solar cells for free, and when you realize that, oh, it's pretty good, I will buy it, and the government give you the discount, you will buy and more people will use it.
So of course there's some limitations with this drawing. So first off, it would be this guy right here. Like he said, it says 12 people, 60 miles per hour. We feel like that this it's a limitation because it doesn't really relate to the analogy. Like it going 60 miles per hour doesn't really relate to solar cells. I mean, you could make the argument that this is about voltage and current, but that doesn't really, like, where is it going, right? It's just 12 people and 60 miles per hour. And another limitation would be the 24/7 sign. Like, of course, Lena did say about like the sunlight or yeah, like how it can be interpreted like in a different way because sunlight is not 24/7. Well, yeah, obviously, but like yeah. So yeah, 24/7 that could be interpreted in a different way. And of course, here the coupons. It's at first this is a limitation because at first we really thought it was just confusing because it says get on the ride for free and then that says get a coupon, so like does it cost money or not? Like we were just confused by that, but yeah, now we understand that it's a government subsidy, but it can be very confusing to interpret. Thank you.
Thank you.
Thank you.
Okay, questions from our audience.
So I agree with you that I think that the 12 people, 60 miles per hour is meant to represent current and voltage. Can you then explain what is the difference between current and voltage and why do you think that this doesn't quite get there? And do you have an idea of something that could be used to show that analogy in this drawing?
Of course. So current is basically the amount of, I would say, let's just say power, like the amount of power, no. Actually, that's not very okay. So power would be voltage. Actually, the voltage would be so basically like let's say the potential for the amount of energy to be transferred, and current would be, I would say, the rate at which the energy is flowing. I would say so, and I think that to apply voltage and current to this would probably have to be to have this roller coaster thing powering something. Instead of just showing us that there's 12 people, 60 miles per hour, because it going 12 or 60 miles per hour doesn't, it doesn't. Well, because the solar cell is all about powering something, right? And then it going 60 miles per hour isn't really powering anything. So if it puts something that the roller coaster could power or something like that, then I would think that the current and voltage would apply.
Could they perhaps have drawn another roller coaster, and how might you represent current and voltage in a separate roller coaster that would show how it relates?
I would have to say maybe you could use like the speed of the roller coaster. Maybe you could use that as, let's say, I would say the speed is probably, given the situation, is probably okay. I feel like this is just really abstract because I don't really know how a roller coaster is going to power something in the first place. So I don't know what speed would represent.
You can let some of your teammates help
Can I
you.
add something? So for me, if I was me, I would like draw the roller coaster from the top to the end so that the height would be the voltage, because it's like the potential that the energy potential that the roller coaster can have, and the number of people, now I get it, like 12 people would be the current, the number of electrons. So I would draw like 12 or 10 people like going down, and I'll write like 10 people, and then the height. So the height would be the voltage and the people would be the current, and I would like change it, like if I have two roller coasters.
Absolutely. If you just, people is a great analogy for current, but if you change from speed to potential drop, that would be a really great analogy for voltage. So what else would you change if you wanted to reflect the solar cell? It's a beautiful drawing that shows a lot of great stuff, but there are some really simple things you could change that you guys commented on.
So at first we were really confused if the people were electrons or photons. from the light, because the solar cells, how it works is the light photons go through the electrode, and then it gets converted into energy by the move of electrons. But then we get the electrons like move through all that process and then go out, but then we don't see the light directly in this like picture. So if we could put more features of photons or light as particles in this picture, we would really like it. So
where are the photons?
I would say because so like she explained, the theme park is basically the sunlight and like the photons, because you know how the light excites the electrons. So we were thinking, oh, maybe the theme park is the representation of the whole thing and how it excites people when you're in a theme park.
Well, so the people, as far as I can tell, they exit at the bottom and then they enter at the top. So what takes them from the bottom to the top?
The energy of people.
In the picture?
The roller coaster?
The roller coaster takes them from the top to the bottom.
Mm-hmm.
What's taking them from the bottom to the top?
Are you saying like the buses that
I think it's the buses.
Yeah, the buses are the iodine or iodide, I think, because it's like bringing in electrons. That's what we think anyways.
Yeah, it's an analogy.
Yeah.
Okay, I'll let other people ask questions.
Any other questions from the audience, please? You don't want me to make aggressive eye contact with you until you ask a question. Or else Professor Tolbert's going to keep asking the hard questions.
We're open for questions, so it's okay. It's okay.
Okay, this is my plea to the parents. Okay, so I've been a parent at a lot of these things. Your job is to ask any kind of question, but this is actually a real job for all the parents. Every time you listen to one of these things, you have to be sitting there like, I'm coming up with a question. I am analyzing what they are saying, and I'm going to ask a question, because honestly, if you don't, I'll just keep going.
How does a coupon work, and how do you earn it?
So essentially, I'm pretty sure they try to like show that the government incentives. So like basically, if you didn't know, China has all these government incentives for owning solar cells, and it kind of drops the market price of solar cells. So basically, it kind of incentivizes people to buy these solar cells, basically.
Okay, great. And then lastly, who is our artist? All right, your name and anything they didn't cover.
Hello, I'm Spencer Kosov. I'm from Los Angeles, California. Firstly, I just want to say you guys did a really good job of covering my image. And I thought your criticisms were really great. And you also interpreted like ways that I didn't even intend. Like, for example, the infinity of the roller coaster for being like the replenishing energy. That wasn't even intended. And I also agree with your criticism of like the 24/7 theme park. Like obviously light is not 24/7. I was kind of just trying to show that it's like a renewable and sustainable source of energy. And like just to clarify a couple things. So I had intended that the two like workers putting the people on and making them leave were like replenishing, like that was kind of the iodine. And I mean, the people, it also wasn't super clear because the dye and the electrons are kind of with each other. So I was intending for the seats to be the dye. And then when the people who are the photons get inside of the seats, they like excite the seats in a sense, like the electrons, and that causes it to be powered. And then the roller coaster track is the electrode because it like conducts the electricity throughout the circuit. That's about it.
Thank you. All right, and thank you, Group 2. Did you want to do an intro right now? Okay, so before we move on to group 3, Professor Tolbert is here, so we just want to give her a moment to say a few words.
Okay, sorry, I apologize for missing the first few. I was stuck in a meeting. I just want to introduce myself. My name is Sarah Tolbert, and I'm a professor in the Department of Chemistry and Biochemistry and in the Department of Material Science and Engineering. And I am the official instructor of record for this class. And so I'm very pleased to have had your students here at CNSI for a week doing science with us. And we'll talk a little bit more at the end, but I just wanted to strongly encourage parents. The whole philosophy of this is to learn how to explain science to people who may not be familiar with the concepts. And that's why we're using everyday analogies to explain concepts. So the less you understand, the more you should ask questions. Because the less you understand, the more you are the target audience of these presentations. And so what I can tell you is when people go out into the world, undergraduate students, graduate students, young professors, the thing that scares everybody the most is, what if somebody asks me a question that I don't know the answer to? And the only way to overcome that fear is just to stand up there and ask questions, answer questions, and realize if you know the answer, you can answer it. If you don't know the answer, you can still say something related to it, and the world does not end when you don't know the answer to a question. So giving your students an opportunity to answer questions is one of the most important parts of this whole final demonstration. So please be a part of asking those questions so they have an opportunity to answer. And yeah, theme park, open sunrise to sunset.
Okay, let's move on to group number 3, please.
I'm Saya, I'm from Indiana, I'm a rising junior.
Hi, I'm Natalie, and I'm a rising senior, and I'm from Los Angeles, California.
And I'm Zach, I'm from Taiwan, and I'm also a rising senior.
So I'm going to start off with explaining what we literally see in the first row. So first we see a plant health scale on a 1 to 5 level, 1 showing no color, which determines poor health, and 5 being the darkest, showing good health. And we see 3 plants being tested, all different colors. And the first 2 do contain plant food, and that results in some color, but we see the plant food for the third one is sold out, so that results in no color, determining poor health. Then after testing this out, this individual determines that the plant with color is a good thing and the plant with no color is a bad thing. And then we see him testing out different plants, and he's measuring different amounts of this plant food, and we see with no plant food, the plant is in poor health, and with the most plant food, the plant results in good health.
Okay, in the second row, we have this guy, and he's mad because it's taking too long to grow the plants. And as you can see, without the water, the plant takes a super long time to grow. And then once he adds the water, though, it takes a quicker amount of time for the plant to grow. And then in this one, he's trying to figure out which plant he has, but he can't see it because it's in the dark. But once he puts it in the light with the flashlight, he can tell that it's plant 4.
And finally, in the last row, we can see that pesticides are harming the plant. So the person, he introduces ladybugs to, which are natural predators that consumes the pests to prevent the plant from denaturing. So the science concept that was analogized here was biosensor. So when the person discovers that the pests are harming the plants, it serves as a signal to the sensor, and then by introducing the ladybugs, which captures a specific components, the pest, it serves as a transduction and the result to this system. Yeah, and however, there are always limitations to analogies. So should we introduce it?
I'm also going to mention the scientific concept in the first row. Oops, sorry. Okay, there you go. So this represents a colorimetric sensor, and what that is it determines different concentration levels of an object by looking at its colors. So in here we could see by looking at the different levels, different colors of the plants, we can determine the level of its healthiness.
And in the second row, the first group of panels represents enzymes. So what enzymes do is they decrease the activation energy for reactions, so it takes less time for the reaction to take place, which, as you can see, the water would be the enzyme. So without it, it takes a really long time. But then once you add it, it takes a faster time. And for the other two, we think it's a colorimetric sensor. So he's trying to figure out which plant or concentration he has, but he can't see because it's in the dark. But once he turns on the sensor, or he can see what the concentration of the plant he has is and what it corresponds to.
And the limitations in the first row is that this idea of the plant containing no plant food is kind of repetitive. We could see it almost 3 times. And also, there is no such thing as plant food, but kind of controversial, but yeah.
And the limitations for the second row, too long, since it's not it's kind of separated from those two, they're not really the same panel. It could be interpreted as absorption. So some wavelengths are too long for specific molecules to absorb. So, but the clock does help with that. But since it's a different panel, it's kind of confusing. So I guess it could be interpreted as wavelength also. And also the dark is kind of misleading, because usually with colorimetric sensors, you add a substance and then the color shows up instead of just turning on a light.
Yeah, and lastly, we think that the last part, it's quite obvious and straightforward. Since ladybugs eating pests are kind of common sense, I guess. So there's no limitations for this. Yeah.
Okay, questions from our audience, please.
So one thing that you guys did in your experiment was, so you have the color changing element of it, but at some point you guys tested unknown samples, right? So I think that is being depicted here. So can you describe the method that you used to then determine the concentration of the unknown samples with the color sensing, and maybe which panel is showing that process, or which set of panels is showing that process?
I think these two in the middle row, the last two, because we used a standard curve, and he has an unknown concentration as the plant he has, and then he uses that set of different plants to determine which one, which is kind of how you use standard curve to determine the molarity of an unknown concentration.
A comment for everyone. Remember that a lot of your audience did not do these experiments. So please, in the process of explaining, give an overview of what was actually done so that the audience can understand. So don't only explain to the insiders, explain to everybody, integrate what you did into your description of the picture.
So another question I have is, we actually, I think, interpreted the bottom set of panels a bit differently. So I guess going back to relating to what you actually did in the experiment, can you describe what materials you were actually using to do this sensing, and why that material can be challenging to use, and then what you might do to overcome the challenge of using that material? So then why then did we interpret that bottom panel differently?
Okay, so we use enzymes, and we put them in nanoparticle beads. And the trouble with enzymes is that they can denature, so we put them in the beads to prevent them from denaturing, so they can actually show the results of the experiment. So the bottom panel, I guess the eating the plant is the enzyme denaturing. So, and then once you put the ladybugs on, or like the nano bead properties, it prevents it, the enzyme or the tree from denaturing or being eaten.
Yeah, just the different measurements of plant food given to each plant.
And how does that relate to the experiment that you did?
For the experiment, we put different kind of concentrations to the little
Concentrations of what?
So the experiment, we use different concentrations of sugar stock combined with water, and we drip it into the well to to kind of make sure how sweet is the unknown product, like the drink we usually drink. So like the number scale ruler is kind of like representing the different concentration. Like 1 is like the lowest concentration, and 5 is the highest. Yeah.
So just to clarify, your biosensor was used to detect sugar, correct? And so how were you determining how much sugar was in the solution?
Through the color changing, if the bead turned, so the bead was supposed to turn to pink, and for my group, our beads turned different shades of pink, so that's how we determined the different concentrations of sugar in each.
So more sugar means more pink.
Yeah.
And so when they're adding more plant food and
Better
it's
health.
becoming darker, that is the analogy to the experiment. Okay, now we have a question.
What does the Fore with the exclamation mark, what's the excitement around that? I must have missed that. What does that mean?
So basically, like on a standard curve, which is what we use, I talked about it a little bit earlier, which is what we use to determine an unknown concentration. Basically, the plants that are like on the ground is the standard curve, and he's using the plant he has, and he's kind of like lining up in his brain like which color of his plant is the same as the color which plant on the ground. So he's like, oh, it's number 4, so it's this concentration.
Another analogy to kind of explain this better is like a puzzle piece. With the darkness, he can't really find the missing piece. So then with the light, he finally matches the color of his plant to the color, to the number 4. So they're the same color.
Okay, great. And who is our artist?
Hi, I'm Shannon. I think they explained it perfectly, especially like the bottom panels. They understood it the way I meant it. And the only thing I want to add is that I just Googled it, and plant food is a real thing. So, just FYI. Yeah, that's all I have.
Great, thank you guys. All right, group 4, please. Where's my... Oh.
Okay, if there's a debate about plant food, can I just say that nitrogen, phosphorus, these are required elements, and they're the components of plant food, and if you give basic elements to plants, they will grow.
Yeah, because I stopped talking after the beginning. Oh, cool, yeah.
Hi, I'm Miles Aguilar from Los Angeles.
Hi, I'm Isaac. I'm from the Bay Area, and I go to Mission San Jose High School.
Hi, I'm Ellie, and I'm from Irvine, and I go to Irvine High School.
Hi, I'm Ryan. I go to San Diego. Wait, I'm from San Diego. I go to Canyon Crest Academy. I'm a rising senior.
Who here has a phone?
Wait, you on your phone? Can you hold it up for me? Like you're literally on your phone. Hold it up for me. In the white shirt. I see you. You were on your phone. Hold up. Thank you. That's exactly what I need. Okay. So in that phone, there are dozens of chips. In fact, in that speaker, in this computer, dozens of chips, right? And so that's all to say that chips are ubiquitous. They're everywhere. But unfortunately, I feel like they're one of the only things that, while being everywhere, we barely know how they work or how they're made. So to answer this question, which is called chip fabrication or chip fab, basically how chips are made, we ran an experiment yesterday that allowed us to create our own chips. Now, while the process we used to create our chips was crude, the same fundamentals are used down in industry, right? So understanding how we created our chips helped us understand how big industry makers make their own chips at smaller scales. Regardless, it's a complicated process, so we were tasked with creating an analogy that can visually depict what's happening when we were making our chips in much simpler terms. I'll let Isaac dissect this one.
Sure. So in the first top panel, it's a 6-step process to creating our chips. So the first step was applying the nail polish in this diagram, and this was symbolized in our experiment when we coated the copper circuit board with photoresist. After that, the diagram shows how you attach a stencil or a cover on the nail to make the nail design more precise. In the same way, we aligned the photo mask to the circuit board, which allowed us to create the designs for the wires. Next on the diagram, it shows a hand with nail polish, and it's placed under a UV lamp. In the same way, we placed a mask and the circuit board assembly under a UV lamp. This created the circuit imprint on our copper plate. The fourth step was the stencil was removed from the hand, and for us, that was the development process. So the photoresist and mask were removed from the circuit board, and the copper was dipped in developer solution. The fifth step was using a Q-tip, and the Q-tip with the nail polish had nail polish remover on it, and it was used to get rid of the unwanted extra nail polish. In the same way, this was our etching process, because to etch the circuit into the board is dipped into etchant solution, which dissolved our unwanted copper. And then finally, the last step was adding oil onto the nails to clean up the design. And for us, we cleaned up the circuit using an acetone wipe.
And in the next row down on the left side, we see the nail on the right being painted with a smaller brush, which allows the paint to be more detailed and like better designs, and in comparison to the right nail being painted with a bigger brush. So this talks about the idea of feature size, because feature size affects function, since as we decrease feature size, it increases functionality. So with the smaller brush, you're able to paint like smaller details, but also being able to still paint like larger designs. But on the right side, it can only paint like larger designs since the paintbrush is bigger.
Okay, and then the picture on the middle right, it shows two hands. On the left, it's a big UV lamp, and then on the right, it's a small UV lamp. So the diagram shows how the larger UV lamp is better for setting the nails more quickly, because you can fit the whole hand in instead of just one finger. So this is an analogy for resistivity. So what is resistivity? Imagine a conductor as a tunnel and electrons like cars. With a one-lane tunnel, cars move more slowly as they don't have space to move around, but then with a 4-lane tunnel, cars move more quickly so they can switch lanes and speed up. In the same way, wider conductors with a larger cross-section area are less resistant to electron movement, or they have less resistivity.
And then in the next row down, you see in this analogy, the left side is painting all the nails and putting it into the UV lamp all at once. But then on the other side, it shows painting each individual nail and then putting it into the UV light individually. So this process takes a lot longer when doing each nail individually. So by decreasing the amount of time it takes for a process to occur, it can allow for more and faster reproduction, which makes like industrial scale production more efficient. And then, but one limitation we found for this is that it's a little unclear when describing parallel processing, because parallel processing is doing things 3 at a time, for example, rather than doing it just 1 at a time. And then in the bottom, this analogy, you can see the person cleaning the nail before doing the designs, which allows the end product to be cleaner in comparison to the dirty nail when they didn't clean it. And this describes the cleaning room lab tour that we took. So before entering the lab, we had to like get suited up to prevent any dust or particles from interfering with any of the projects. And so this is important because dust and particles heavily impact like the projects on a nanoscale. But one limitation we found for this one is that in the clean room, like the air circulates constantly, but in this analogy, it only cleaned the nails once.
Okay, yeah. So this drawing was based off of stuff we did yesterday. Something important we did yesterday that's not shown in this drawing is we looked at the SEM. So the SEM, or scanning electron microscope, works by shooting a beam of electrons, and the electrons hit a surface, they get scattered. And based off the scattering, the SEM is able to create a magnified image. This works better than a traditional optical microscope because electrons have a smaller wavelength than light, so the SEM is able to see smaller things. Yesterday, we went to the basement and saw the SEM machine. It was pretty cool, so I thought it was worth mentioning.
Thank you.
Okay, questions from the audience?
So I think there's one additional thing that's being depicted here, and I'm curious if you can interpret it kind of on the fly. So there's the nail that is with the big brush and the nail that's done with the small brush. It seems like they actually cost two different amounts. Like it looks like the nail on the right with the big flower is only $5, and the nail with all the small art looks like it's cost $15. So what do you think the price difference could be alluding to in this case?
Yeah, so I think maybe something that could be alluding to is the fact that when you make things smaller and more precisely, or use tools that are more smaller, precise, although it may have a better result, it often costs more. So in the real world, a lot of our things are limited by how much they cost, and so a lot of times it might not be feasible to use such small solutions.
And I think it also kind of talks about how, like, if it's a smaller design, it takes more time. So it's like talking about like labor costs and stuff like that.
Yeah, that could be it. I could see another interpretation also having to do with maybe the relationship between wavelength and energy. So if that is the case, could you maybe describe it with that analogy?
Yeah, sure. So I think what you're alluding to is like the smaller brush has smaller wavelength, and therefore you can create smaller details. And so as you can see, the smaller brush also has the higher energy cost or higher energy associated with it. And so that, kind of intuitively makes sense, because as you decrease the wavelength, as you have more wave peaks in a shorter distance, your energy inherently goes up, and that might be what it's alluding to as well.
Yes, nice.
So on the bottom panel, I can understand clean nails are better than dirty nails. So what happens if the nails get dirty? Do they malfunction completely, or efficiency drops to 50%, 30%?
So like in this analogy, it talked about like the clean room. And so like in the clean room, we had to like tie back our hairs if you had like, and I think it kind of affects the, because like dust and particles are a lot bigger in comparison on the nanoscale. So like small things like that really affect the like numbers that we take from it. Yeah.
So first to follow up on that, did anybody, when you were doing any measurements of the resistivity of your wires, find that any wires were open circuit, had no conductivity at all?
Yeah.
So why do you think that happened?
That probably, there's a couple reasons that could have happened, right? Could be contamination, like it says down there where it's like dirty. It could have also been over-etching. We could have over-etched the copper, and therefore it would have been an open circuit. But I think more related to contamination, right? If there is contamination that could cause an open circuit or unwanted shorting. So it's just that panel on the bottom is just telling us that it's important to avoid contamination.
Right. So the two are related, because over-etching means basically you just etched your wire till it broke. But if there's a place where there was a dust or a defect, that's where it will etch faster. And so you're more likely to etch it till it breaks. So I just had also one comment or one question. So you said that, and maybe I don't understand nail polish, so I'll just apologize to start. But you said at the beginning that putting down the nail polish on the nails was putting down your photoresist. But in the end, you're making patterns in the nail polish, right?
Yeah, so I think this may have been one of the limitations. We kind of saw the nail polish in two different ways. One as applying the photoresist because that was one of the steps in the process. But at the same time, we noticed how it showed clearly that there was some sort of cover on top of the nail polish, and we assumed that would be alluding to this step of applying the mask. So we thought it could apply to two different concepts at the same time.
So what would be just another possible set of layers if the nail polish was not the photoresist? What else could the nail polish be? And what could the nails be?
I think it's safe to assume that the nails are the substrate or whatever is on the
Yes.
bottom, just because you would
You're
never
not
wanna,
doing anything to the nails.
Yeah, you wouldn't
Thank
want to.
That would hurt.
Etch into your nail. I guess if we're saying that the polish is not the photoresist, then it would make sense that the polish is the copper or whatever conductive material you have, and then on top of that you have your mask or photoresist.
Yep, because you're putting patterns into the nail polish, which is the same as putting patterns into the copper. You're not putting patterns into the nails. Thank you very much. That's good. That would hurt. Yeah, good job.
Okay, and who is our artist for this one?
Hi, my name is Kayla Martinez. I really thought they explained my analogy very well, and all the limitations are definitely true. The nail polish definitely should have been the cover is, because I end up taking that off in the end, which is a very good recommendation. Thank you. Other than that, they explained everything pretty well. I really don't have any comments, so thank you. All right, thank you.
Is this someone's phone? Phone? Okay, group 5, please. Okay, I just want to give context for this one. We had an experiment this morning, okay? So they did a lab this morning. This was called Supercapacitors. And so we had 6 lovely volunteers volunteer to draw a drawing during lunchtime, okay? And then they swapped with each other. So they're still describing someone else's picture, but they just did this during lunch. And they just learned this experiment this morning. So extra props to these guys for volunteering and also for, working with our graduate students to really very quickly understand this topic that we're going to talk about.
Hi, my name is Tyler. I'm from Irvine, California.
Hi, I'm Daniel. I'm from Fremont, California, and I go to American High School.
Hi, I'm Ryan Chang, and I'm from South Pasadena.
So today we did a topic on supercapacitors. Sorry, supercapacitors today, and we deduced that from this picture. And we did a whole experiment on building a supercapacitor with all the wires and the carbon all together.
All right, so I want to give a brief overview of our experiment first so that everybody gets what we're talking about. So what a supercapacitor is essentially a capacitor. However, it stores more energy. But what is a capacitor, you may ask? It's essentially a battery, but stores much, much less energy. The problem with the capacitor is it stores like really less energy. However, it's really fast. With a battery, you can store a lot of energy, but the problem with that is that the energy transfer is really slow. So what we did was we created a supercapacitor with stainless steel squares, and we had activated carbon, which acted as what stored the energy. We also had a circuit on a breadboard, which allowed us to look at an LED and see how much power we were able to get through.
So when we're looking at this analogy here, we first see there's 3 separate columns, and each of them are going down. So the first column we see here is it's nighttime, he goes to sleep, he takes 8 hours to sleep, and then in the morning, he wakes up and he runs a very long, 3 miles at 8 minutes per mile, which I think is pretty fast. I mean, for me. Second column is we see an oven and there's a cake inside. It takes 2 hours to bake the cake, and then the guy eats it, and then he runs 1 mile for 5 minutes. Pretty crazy. And then third one, he makes cupcakes, multiple cupcakes for only half an hour, and then it looks like when he eats the cupcakes, he can only run for a quarter of a mile before he has to eat another one and gain that energy to run again.
All right, so I want to explain the scientific concepts behind this. So what we believe the first column to be is essentially a battery. The person sleeps for 8 hours, which is a pretty long time, and he's able to run a decently long time at a somewhat slower pace, but it's 3 miles, which is still pretty long. For the second column, we have in a cake baked in an oven for 2 hours, which we believe to be a supercapacitor. That's because he eats the cake all in one go, and he's able to run a mile really fast, which basically means that the energy was able to go out a lot faster.
Okay, so for the third one, we believe that the cupcakes are capacitors because it takes less time to bake it, a quarter of the time of the cake, but each cake only provides a quarter of an energy to run a quarter of a mile. And then the second box is related to, well, it's the amount of distance you can run, but we actually learned about a realistic scenario where certain places are rolling out buses that charge when they stop, that they use capacitors to do so, and whenever they stop, it charges for the next few stops the energy to drive to that, yeah. And then for limitations, one of this could be the surface area, because theoretically more cupcakes would have more surface area than the entire cake. So this is limitation because batteries and capacitors use surface area in order to function. And then finally, this is not really a limitation, but I don't think eating a cake would be good before running a mile.
And then one more thing is that between a surface the battery and the supercapacitor, they are 2 different things. So the battery actually has a chemical reaction that causes the storage of the electricity, whereas these capacitors, they don't have this chemical reaction and are more physical to send the electricity and hold on to them. Thank you.
Okay, questions from our audience.
Hi, thank you for the presentation, by the way. It was very nice. I just have a question on why exactly, or like, what is the exact reason why a capacitor is faster than releasing energy than a battery, and why is like a battery slower?
So what we have here is correlation. So in scientific terms, we have specific energy and specific power. These are actually completely different things. Specific power is the amount of power we're able to get out within a certain amount of time. However, with specific energy, that's how much energy that we can actually store. Capacitors, they're able to get the energy out a lot faster because they're a lot smaller. That's the correlation here.
Okay, so I'm not entirely sure about that I fully understand the flow of the panels, but if we just ignore the first column for a minute, if you just look at the second 2 columns where you start with an oven and you have an amount of time, can you just contrast those 2 columns in terms of batteries versus capacitors?
So without regarding the first column, correct?
Yeah, let's just forget the first column for a minute, because I'm confused by it.
So is what you're asking like what's the difference between the battery and the capacitor with the two columns?
Yeah.
The second and third. So what the second and third column represent are both capacitors, since they're different from the first column, which is a battery.
Which is why I want you to think about maybe explaining it differently. So I want you to ignore the first column and just describe the second, the middle and right columns. Because I think that you can map those two columns onto batteries and capacitors.
Okay, so for the oven there, it takes 2 hours to essentially charge the battery, right? So that cake would be the battery with all the energy stored inside. And then I guess maybe that chemical reaction of him eating it, going down the stomach and all that, doing all the processes in there, would be it getting released into the person and giving him the energy to essentially run faster. Whereas in the further right one, it looks like this one is the more less energy being given to the person, which is shown as he's only able to run that short amount of time before he needs to eat another one.
Yeah, I think that that's an analogy that makes sense,
Okay,
because
without the first one.
yeah, it's a bite size, it's a fast charge, but it's a short amount of energy. Whereas the cake, it's many panels of eating, and then you can run a long distance. I'm not quite sure how to integrate that with the first column, and so maybe you guys have more ideas, or maybe the authors can help us think about that. But I think what you just described makes a lot of sense in terms of the concepts of a battery that sort of stores things in the bulk of a big material, as opposed to a supercapacitor that stores energy on the nanoscale surface of a small material.
I think it's because we had 3 different things we learned about: the battery, the supercapacitor, and then the regular supercapacitor that's super fast. And that's why they tried to show 3 different ones there.
Thank you. Lovely presentation. Very informative. My question is, so we don't know the setup to your experiment or whatever equipment you saw this morning. I'm curious how you were able to measure the energy and see experimentally the difference between the battery and the supercapacitor. What sort of sensor or something were you using to observe it, and what did that look like? Thank you.
All right, so thank you for the question. So we didn't actually use batteries in our experiment. So what we did was we first created our supercapacitor. This was made with stainless steel squares and the carbon so that we could store the actual energy. So how we actually measured the energy was through a circuit. So if you don't know what a circuit is basically a full circle of electric components that's able to give you some like physical feedback. So we used a breadboard, which is where you usually build circuits on. We were able to wire up our supercapacitor to our breadboard, and with a Fore switch, which is just something that maps out our energy with the switch. There's 4 different buttons that you can press on it, or there's 4 ways that you can get information from it, which maps out the electricity. We had an LED on top of the breadboard, which showed us the brightness basically, or how fast the blink of the LED was. So with our supercapacitor, we only showed like a really fast blink, and it was pretty dim too. However, we were still able to capture it, which showed us that we didn't really get that much energy, and it was a really fast like electrical reaction basically. And another thing that I would like to point out is that if we were to wire multiple supercapacitors together, we would get more energy and therefore a brighter blink.
Okay, and so our artists were another group that volunteered to draw this one today. So did you guys have anything that you wanted to say about this one?
Hi, I'm Avi. I'm one of the people that helped draw this picture. And I think we might have messed up a little bit with regarding the time and the surface area, because we know that capacitors are the fastest of battery supercapacitors and capacitors themselves. So technically that would be the cupcakes. But the thing is, supercapacitors we know have more storage, and the cupcakes have more surface area. So I think we messed that up because technically the supercapacitors would be represented by the cupcakes, but also the 2 hours in time. So it got swapped there a little bit. So I think that's what made it a little hard to kind of dissect this picture. But good job.
All right, group 6, and then we will take a short break.
Hi, I'm William, and I'm a rising junior, and I live in LA.
I'm Nick. I'm also a rising junior. I'm from Chicago.
Hi, I'm Shini. I'm from Thailand.
Okay, so first of all, if you look at the top of this cartoon, you can see that it is nighttime and there's a detective trying to find like the wanted criminal, and he's looking at 3 suspects, and there's also like a wanted sign on the wall. So this drawing is an example of indirect measurement, and indirect measurement is data which is collected on one specific variable to find data on another measurement. And scientists use this because it is beneficial, and it's used when they have to find something that cannot be measured. And in this cartoon, since it is nighttime, the detective cannot really see any of the suspects. And by looking at the wanted poster, he sees that there's the guy he's trying to look for has a crown on his head, and then he observes the shadows, and then he sees that the guy on the left is wearing a crown, and then that's how the detective finds the wanted criminal.
So in the second row, we have the detective looking at what seems to be footprints, and he's looking through a magnifying glass, but he can't seem to get a very detailed or zoomed in image. But to the right of that, there's an ant who is looking through another magnifying glass, and he can get a more zoomed in and detailed image. So one concept this could represent is the atomic force microscope that we looked at. And this is a microscope that uses a little atom on the end of like a spike to feel a molecule to get like a topical image of the shape of that molecule. And it's more useful when looking at the nanoscale than a normal microscope because the wavelength of light limits measuring things using light in a normal microscope when it gets below the minimum wavelength of visible light, which is about 380 nanometers. But one of the limitations to this drawing is that an atomic force microscope needs to touch what it's measuring to actually measure that, and the ant isn't actually touching the footprint, or at least not what it's using to measure isn't touching. So that could lead us to think it's maybe another concept.
Yeah, so the thing is, initially I didn't agree with him because I thought that as you can see that both the human detective and the ants detective, they are both using the magnifying glass, which requires light for us to be able to see the object closer. So I think that this was similar to the concept that we learned about how light could be used to measure both big object and small object in like nanoscales. And additionally, like the AFM mechanism doesn't really align a little bit with the picture. So we think that this is a bit of a limitation because it might create a little bit of a confusion. So if the artists truly want to depict the concept of light measurement, they might need to use a different object with one being super big and the other being small. But in the end, as a group, we believe that the artist truly was trying to provide the concept of the AFM, which is why we think that maybe just by substituting the magnifying glass for something else would be more clear. And let's move on to the third picture, where we can see that on the left side, we can see that the detective are agreeing with his partner on the direction they're walking, thus why they're walking fast. Now, for the right side, you can see that he's arguing with the other person, which is why they're kind of staying in the same place.
So we think this is representing the concept of interference, where on the left it's constructive interference, where waves are in sync. So they combine the two waves to create a wave with the sum of the amplitudes of the waves, and that leads to a larger wave, whereas on the right side, the waves are counteracting each other, they're out of sync, and the difference of the wavelengths is the resulting wave amplitude. So nothing gets done, and the distinguished gentleman and his partner cannot move.
One limitation that I found in this entire cartoon was it's supposed to be about a detective and him doing his job, but in the last part, he's not really doing his job. He's just with his I guess wife. I don't know. It's not that important, but I don't know. I just found that weird.
The pictures are a little unrelated. Which can be a little confusing if you think they're combining to create concepts.
Okay, questions from the audience, please.
You guys did a really good job of explaining this. It's going to be harder for people to come up with questions. Just telling you.
So it seems like that was an excellent explanation. I was just curious about what kind of techniques that people uses, as in this nanoscience detective. Could you just explain some of the instruments that you guys learned throughout the week, and maybe just give a brief explanation about how it works?
Okay, so some of the main tools we learned to measuring things at the nanoscale that are better than a microscope because they can measure things that are smaller than the smallest wavelength of visible light are the AFM that I already described, which uses that little molecule to feel around and get an image, and electron microscope, which shoots electrons at molecules to get an image of them. And it works because the wavelength of electrons is a lot smaller. It can get way smaller than the wavelength of visible light, so you can get a more detailed and smaller image.
So then, based on this, what are they actually depicting? If you say they're not depicting an AFM in this picture?
I think they are, but I think they should have swapped out the magnifying glass for a different tool to demonstrate that one of them.
Okay. Given that this is the picture, given the whole week of things, what could they have been drawing?
The man versus the ant.
So the ant's smaller than the man.
What does that represent?
So the man's a light microscope. What's the ant?
An electron microscope?
Yes.
Yeah. We looked at the concepts for the day that they were drawing, and that wasn't on it. So.
If you didn't know about electron microscope so much that day, but still, once you got the picture, you can.
Yeah, true. That would make more sense.
Okay, just for the sake of time, we're going to move on. So who is our artist?
Hi, I'm Lena again. So I fully accept the limitations. I should have switched the magnifying glasses to another measure that depicts the AFM better. But I wanted to point out that the last row is actually the detectives going to the investigation site together. So if they match the direction, then they can go faster. But if they're not matching, then they can't move at all.
Thank you. All right, I think we all need a little bit of a leg stretch and bathroom break. So we're gonna take a 10-minute break. We will be back at 3:44.
wiggling. So it scans along, wiggling, and you can image on the frequency or actually the phase. So you drive a wiggling, and when it interacts, instead, if you drive it 1, 2, 3, it could go 1 down, 1. Like it can be a little slower than the driving force. And so you often actually image on the phase of the wiggling, and that gives you very weak interactions about the feeling of the surface.
Right, it's like measuring the dimples on the surface.
Yeah, right? Yeah, so that's called non-contact, which is what most people image.
Yeah.
You can also physically touch it and scan along the surface. And then when you physically touch it, you don't usually wiggle, then you're just a solid contact.
The other question I had was the ladybugs. Okay, so the nanomaterial that's, I guess, is encasing the enzyme, is that right? Or
Yeah, it's a nanoporous polymer.
it's
a nanopolymer.
It's organic.
Yeah.
I'm just curious because many years ago, did they use things like detergents and lipids to sort of like
Yeah, people have used all sorts of things like detergents and lipids to encase and stabilize. The COVID vaccine is lipid stabilized. So they're still doing it. That works. Yeah.
Well, this is really interesting. Thank you guys. I don't know, my kid is.
Oh, good.
Were they commuting? Were they staying in the dorms?
Oh no, we live local, so.
Oh, so they're commuting. So they got to tell you every day what they were doing.
I know.
That's exciting.
And I couldn't believe it. He actually had to do homework.
Yep.
Yeah.
So you can actually post transcripts, and I told them all that you can go to the UCLA registrar's page, and you can download a UCLA transcript. You can give it to your high school, and they will attach it to your high school transcript, and they'll send it to colleges with your high school transcript. So you can have an actual UCLA class as part of your high school transcript. So since it's actual UCLA credit, we have
Okay, let's find our seats again so we can get started. We have food after this, so hopefully that's motivation for everybody that we wrap up in a timely fashion so we can get to food after this.
I just asked that you guys know what group number you are. As group, 7 is finishing, group 8, be ready to go, because we are a little behind. So we're going to try to be a little more efficient.
All right, so next up we have group 7. Come on up.
Hi, I'm Naoya. I'm originally from Japan, but I go to school in Connecticut.
Hi, I'm Annika, and I'm from San Jose, California. Hi, I'm Laura. I'm from Brazil. Okay, so first we're going to explain the literal meaning of the picture that we see over here. So, well, overall, we do see a daycare with parents bringing their children to the daycare, who are then led by the daycare instructors into the playground and into the daycare itself. We do see the kids playing with a ball there, and then along with another daycare instructor who's trying to keep things a bit settled there, I guess. And then there's also a play structure where they're taking their turn and going down the slide. There are 17 kids today, and that number will be important later on.
So basically, the idea that's being covered here is of solar cells. But first, before explaining how it is related to that, I'd like to start explaining how the solar cells work. First, the sun goes through an electrode, that is the glass. We put one on top and one underneath it. And then the light goes through that, and it excites a dye, creating an electron. And then the electron goes to the TiO2, which is a semiconductor. And the semiconductor is responsible to take these electrons to the circuit. So, and then the last part of this whole cycle is the iodine, and the iodine is responsible to give more electrons for the dye to keep on creating electrons for the circuit. So how's this related to this whole situation? Basically here, this is a parent. The parent represents the sunshine, because the sunshine basically brings the energy. In this case, it is bringing the electron. We're talking more about this later, I guess. And then the electrode is the entrance, the door right there. And then that first instructor in the daycare, that one represents the dye that is bringing in all the electrons. And the one that's controlling represents the TiO2, because the TiO2 is the one that's responsible to actually control and take them into circuit. So in this case, the circuit would be that the kids playing out there, that's the circuit. And the iodine is represented by that phrase up there that says, I can't wait to bring my brother next year, because it represents that there will be more people coming, so it is cyclical. This also shows that it is renewable energy. That's an important point. And the kids represent the electrons in general. And here where the kids are entering, you can see current and voltage represented, because the amount of kid changes the current, and the voltage would be like the energy the kids put on to get in. Basically, that's it.
And so the kids rolling the ball, we also thought that that could have represented the spin coating, which was one of the methods that we used. Yeah.
Okay, now, although many of the concepts about solar cells are very well illustrated, there are a couple of limitations. Dye is supposed to bring the electrons, but in this case, the sunlight or parents brought in the electrons. And another limitation is that the spin coating is supposed to result in another larger substance, in another layer of substance being attached to the tool, but in this case, there seems to be nothing added to the ball. So that's our presentation.
Oh, and another concept that we learned on this day, which isn't represented in the drawing, is I guess how it's like connected to the economical side. And I think another group said this earlier, but one of the reasons is because of the government subsidies that basically reduce the costs by like a pretty large amount.
and also has the effect of like silicon limitation. So like obviously silicon is a limited resource and there aren't infinite amount of it. And also from the pollution that are like caused from the production of the solar cells.
Ooh, we've got a lot of audience participation.
Quick question. No, nothing about any of this, so I apologize if I missed it. So you were saying the mother, as a limitation, being representing the son, is bringing them to, daycare. Why does the mother not represent the iodine, like you said? What made you make that distinction?
Well, the mother could also represent an iodine, like she's also gonna be probably the one who brings up, but also she has to be the sunshine because that's where the energy come from, the energy that brings the kids in. So she has to be the sunshine, but it could be a good point that she could also be the iodine if it is like that specific girl's mother because she's bringing the next kid. So what matters is that is the person who's bringing the next kid, not the kid that's already in there.
And in general, mothers are sunshine.
Wow, well played, Shailene. So one other concept that you guys learned about on the Solar Cell Day had to do with different wavelengths of light and how solar cells and different types of solar cells absorb light based on, like different wavelengths, how well they absorb. Can you describe like how a dye sensitized solar cell works in that regard versus something like a silicon solar cell? And then with this analogy, if you were to add that sort of wavelength specificity in terms of how well it absorbs, how might you do that?
The thing of the dye, it works because the dye we used was out of, what's the name of the fruit? Raspberries, yes, sorry. Raspberries, and they're red, so it will absorb the green light, and then it will be reflecting the opposite in the color wheel, which is red in this case. So green light is like quite present in the sunlight. So that is why we choose this type, because it will be absorbing more, and the silicon does not do this thing that absorbs, and then the more light you absorb, the more this will heat up, the more this will like create the electrons, basically. And maybe a way of incorporating this in was maybe not having a daycare, having like a high school where you could have like bigger kids. The bigger kids could be maybe other type of wavelength.
Okay, so one of the concepts of solar that, I mean, every drawing captures different aspects is this cyclical nature, which is, the track on the other, where you take things uphill and then they fall downhill, and then you take them uphill and then they fall downhill. Is there any way that you could think to incorporate that cyclical nature in this drawing? Because I think that's the one thing that is not so captured. And so there's many possible answers, but brainstorm a little bit.
Yeah, so we tried to point that as a limitation a bit when we were brainstorming ourselves. But our cyclical cycle that we thought of was in the play structure as well. They were getting the energy from hanging out with their friends a bit earlier, and then they go up the stairs and they go down the slide. So that's kind of the ending of the cycle that we try to pinpoint here.
And at the same time, maybe another way of doing this, as you're saying, it is cyclical. So these kids, they will go back home at some moment. So when they come back to school, that could be also a representation of the cycle.
The play structure is good. That is that kind of uphill and downhill is the cycle of the solar cell.
Why was it important for the 17 kids to be mentioned when there's 20 kids in the picture?
Well, the importance of saying that is 17 kids, it's about current, because the current, basically, it's the idea of how many electrons are passing through the wires. So this would like be representing the current. Now about the number of kids that are actually there, I'm not sure, but maybe the teacher has only counted the ones that has already entered, and like maybe she's missing, like, this one is still getting here, and these two are still not there. Maybe she haven't seen them, just didn't count yet.
Oh, and I think another idea that we had was going back to the picture of like the kids rolling the ball, we said like that could have also been the voltage and basically the current, because the kids would be like the force that would push, or I guess the flow, make it flow, and the ball rolling would actually be like the current, so like the flowing.
Okay, great. So who is our artist?
Hi, my name's Lila Medlin. First off, I'm going to start with 17 kids. I originally drew 17 kids, and then I added the playground last minute and completely forgot to change that number. So I also finished this at like 12 a.m., so I was very tired. I apologize for that. And actually, I like the spin coating. I originally did not mean that for that to be on there. It was originally just supposed to be a representation of force, and how the more force you put, the more power it has. That was simply supposed to be it, but I like that you interpreted that as spin coating. And yeah, that's pretty much it.
All right, next up we have group 8.
Okay. Hi, my name is Kayla Martinez. I'm a rising junior from the South Bay.
Hi, my name is Emma Nakazato, and I'm a rising senior from the Bay Area.
And hi, my name's Marcel Zamora. I'm from Pasadena, and I'm also a rising junior.
This is the analogy that we'll be analyzing today, and this is from our biosensor lab that we performed on Wednesday. In this lab, we use nanoporous beads to encapsulate different enzymes that would be able to detect glucose when submerged into different solutions. This would be a biosensor, as the presence of glucose would invoke a change of color as a response. Then we used a calibration curve to identify the dilution of the glucose in each solution to give a relative sense of how much of it is present overall. These beads were able to show the color change while keeping the enzymes from being denatured in the different levels of pH in all the different solutions. Now, he will talk about what we see in the actual analogy.
Okay, so what we see is we have a baker baking it looks like a pie. I'm not sure, it might be a cupcake, but we can see on the bottom left there's an oven and there's one cupcake in their pie. It seems to be completely fine, and on the table there's another one, but it's not protected by the oven, and there are a lot of flies. And we can also see he's holding up one of them, and it's actually burnt based on what he smells. And on the top right, we see a burn chart, which tells us what color each of the cupcake represents. Okay, so for our first analogy is a calibration curve, which is represented by the burn chart. And so a calibration curve is a general method for determining the concentration of a substance in an unknown sample by comparing the unknown to a set of samples with a known concentration. So you can see on the, like, for example, the first cupcake is completely clear, like you don't see any markings that represents like it's undercooked. Slightly colored is like perfect, and really just darkened is just overcooked. So based on that chart, you can see that the cupcake he has is just completely burnt.
So some other things we saw were biosensors. So a biosensor uses a biological molecule to signal as a signal to detect the presence of a chemical.
So in this, we can see that the person is the biosensor that gives a response of how cooked it is. And in this case, the biological molecule would be like the molecules from the food that are inhaled by the person. And another concept we saw in this lab was the nanoporous bead, which prevents enzymes from being denatured by acids and bases. And it allows the reaction to occur by allowing it to not be contaminated by
or allowing the bead to not be contaminated. And we could see that with the pie cooker. So when the pie is in the oven, it's not contaminated, and it's protected by like the nanoporous bead, which is like the oven. And then when it's on the table, it's not protected, so there are a lot of bugs around it. And another concept that we think we might have seen is absorption spectroscopy, which uses color to determine how much light a sample absorbs, which kind of tells you about like the concentration of absorbing molecules. And so we can see like the chart, and it uses color to determine the concentration of burnt molecules, but this also could have been a calibration curve, as you mentioned earlier. Another thing that we don't see that was another concept was the colorimetric sensor. And a colorimetric sensor uses a signaling molecule to produce a color response. So we didn't really see that here because there was no like sensor that used color.
Yeah, this would be one of the limitations, as the colorimetric sensor was one of the big concepts in this lab, as it showed the different concentrations of each of the beads within different solutions. So we thought that was a very important concept to incorporate within this analogy, so then it could get the full idea of the actual experiment that we did. Yeah, thank you.
So just a couple comments. First, these have to be black and white. And so white, slightly dark, and black is as close to colorimetric variation as one is allowed to draw here. So I think that does cover the colorimetric. The other is a non-science concept that I just have to say, which is it is a pie cooker and a proofing oven. You proof bread, you don't proof pies, but that's okay. We can go with that. So you did, I just want to say you did an excellent job of explaining all of the concepts. And I think that the concepts are very clear. One concept that is not included here is the idea of an enzyme. So could you just talk a little bit, and it's fine, you can't include everything in a drawing. Could you talk a little bit about what an enzyme is and how it was a part of your colorimetric sensor?
So like an enzyme, it's not really used up in the reaction, so it's like not one of the reactants, but it helps like lower the activation energy, which helps reactions occur, and we didn't really see that here, but we did see that in the experiment.
Do you think maybe the pie cooker, I don't know, I didn't grade these or anything. Do you think the pie cooker could maybe be an enzyme? Because like the one in the pie cooker is like more, it has the up arrow, like it's bigger than the one that's proofing method 2. I don't know. Is it like activation energy something?
That definitely could be a possibility of demonstrating an enzyme, but we didn't really take it that way, as it says proofing method, so we just thought it was a way to almost like just protect a pie, I guess, from any like outside bugs or whatever.
Yeah. But I just should add that proofing is a chemical reaction in bread, so that could be an enzyme analogy. Yeah.
Okay, let's ask our artist. Who is our artist?
Hi, I'm Isaac. I'm from the Bay Area, and yeah, I don't really know much about baking, so maybe maybe it should have been bread cooker 3000 instead of pie cooker 3000. I did intend for the oven to also be an enzyme because it helps facilitate the proofing of the bread/pie. Versus the proofing method outside. But I agree with all your other points, and I really like how you analyzed it, so thanks.
Thank you. Okay, up next we have group 9. All right, 3 microphones and a laser pointer.
Hi, everybody. I'm Shannon. I'm from Alameda, California, which is a town in the Bay Area.
I'm Kayla, and I'm from Northridge, California.
Hello again, I'm Spencer Kosov. I'm from Los Angeles, and I'm rising senior.
Okay, so first off, I'm going to be explaining what we see right off the bat. So what we see is a cake with 2 layers of icing, and then they put a stencil on it, and they chill it to, I assume, like, I don't know, make like it's stiffer. I don't know how to bake, but and then they take the stencil off and they scrape all of the icing off except for the area where the stencil is. So then the heart indent is still on there. And then on the left, on the top, it's showing like the different sizes of the stencils and how you can fit more with the like smaller stencils. And then on the bottom left, it's showing that it's more efficient to have a bunch of cakes in the oven. Those are cakes, yeah. And that it makes more money that way because then they can do more at once. And then on the right, it's showing like that if you don't have an air filter or something, that flies will come in and your cake will not be able to, you won't be able to use it. And then on the bottom, it's showing that it's clean if you have the filter.
Okay, so basically on the top like slide, it's representing the process of photolithography, which is what we learned about yesterday. The different layers, the cake, the icing, and the glaze represent different things. So the glaze represents the photoresist, and then the icing represents the copper or the material that you're working with, and then the cake itself represents the substrate, which is basically the base layer, and you don't change anything to it. And in the first step, they're putting on the photoresist, or the glaze in this case. And then in the second step, they're putting on the stencil, which represents the mask. And the mask that you're putting on is basically the design that you want to capture and like block the light from hitting. And then in the third step, they're putting it in the fridge to chill it, which is basically it's the process of exposing it to the light, or it represents that. And then in the fourth step, it represents the development process, which is when you take off the glaze or the photoresist. And then number 5 is etching, which is when you take off the excess material. So in our lab, the etching process took off a layer of copper from the design that you did not want to be there. And then number 6 was the stripping process, where they removed where they had removed the glaze from it to take off the photoresist on top of the design. So it just exposes the design, or the copper design that you created. And then in the next slide, we have the different size stencils, which represents feature size. And the smaller size of the stencils means you could fit more of the stencils onto the cake, which increased the functionality. And then on the very bottom, we have 6 cakes baking per hour, which means more money, and then the 1 cake baking per hour. And then this represents the parallel versus sequential process. And in a parallel process, you have multiple things happening at once, so that way it goes faster, which is important in the industrial process making. So when we went to visit a photolithography lab yesterday in the clean room, and they had the parallel process, so that way things would be made faster. And then versus the sequential, where you do one at a time, it would take a lot longer. And then on the very right, it emphasizes the importance of having a clean room, so then there's no contamination, because when working with nanomaterials, dust particles are like the size of microns, so that way it's much bigger than a nanometer, so that way it would contaminate it.
Yeah, to add on to why feature size with the smaller stencils is pertinent to photolithography. So basically, we're like using light to engrave a design on a circuit and make like an integrated circuit. And what the smaller stencils represent basically is when you're using light, depending on the wavelength of light that you use, you can get like more detail. So if you use a higher energy light with a smaller wavelength, you can get more small detail, and that allows you to fit like more functionality into a smaller space, which is just better when you're trying to make an integrated circuit. And some limitations of the analogy. Firstly, it's a little bit unrealistic, because when you're making a cake, you're not like necessarily removing the icing and glaze after you finish baking it, so that can make it hard for some people who haven't done the experiment before to understand. And also, you can't completely discern like the layers of the cake. So maybe using like some different shading might have helped everybody understand. And that's about it.
So with the parallel versus sequential processing, I see how they've depicted it here, but when you're talking about making parallel versus sequential processing in circuits, like what aspect of it is actually the parallel aspect based on like, you know, your visit to the clean room or you guys learning how they actually make circuits in a real lab? What is the parallel there?
Are you asking like what it means or like an example?
I guess kind of both, right? So like if you're making multiple at one time, like what, like here it seems like they're making multiple cakes at one time. So like what is the multiplying factor? Like is it multiple like individual wafers or like what is the multiplying part?
So what it is you break up a process into multiple steps that can be done all at the same time. So this one isn't exactly doing it because it's one step that's being multiplied, but it's doing different steps at the same time.
I can add on to that. So when we were actually making our integrated circuits, we were working in groups of 3 at a table of 6 people. So when we were like doing the soaking process for like the etching, we had 2 circuits back to back, and that was allowing us to like undergo the process of etching with 2 circuits at once, which would be more efficient than doing 1 circuit at a time individually.
So I wasn't in the clean room with you, so I don't know exactly what you saw, but hopefully you saw some wafers. How big are they? That's the small sizes.
Yeah, there were a bunch of different ones, but some of them were really big.
So the common ones they use now are like 10-inch wafers.
Yeah.
So how big is your phone?
Small. It's probably
And
that
so
big.
what are they making on that wafer? Are they making the chip for one phone?
No.
So can you say more about what they are making?
Yeah, I mean, so they're I mean, I didn't see that well inside of the clean room. I was like a little bit in the back, unfortunately. But I think they were like processing multiple parts on the chip at once, which would be more efficient than doing 1-by-1 steps.
Yeah, the big chip has the active chip for many devices. They're just all arrayed out. And then after they make the whole chip, they dice it. And they cut it up into lots and lots of little chips. So one process, one exposure and whatever makes many chips. So I think that's...
Yeah, so you could have the same mask or the same stencil multiple times on one wafer and then make it that way.
I just want a separate point. I want to commend the comment of so icing and frosting and layers is a really good way for a practical thing for people to think about. But in terms of this whole idea of communicating science to the general audience, you don't usually take the frosting off a cake. And so when that's part of the process, it does make it harder for people to connect. And so in this idea of making an analogy, you want to pick something that actually happens, and that's what makes this so hard, is to find something that actually happens that has the same kind of steps as that you were doing. So good job pointing that out.
I just wanted to ask, I've heard that there might be different types of photoresist. Could you explain what different types of photoresist that exist, and perhaps what this hypothetical glaze is? Okay, there are 2 types of photoresist that we learned, positive and negative. Which type of photoresist do you think glazes in this photo?
Okay. So this is the positive photoresist.
Basically the positive and the negative photoresist. So when you're printing on something, a positive photoresist, like the stencil, for example, is a heart, right? And when you're doing a positive photoresist, the outcome you're gonna get from the stencil will be a heart shape. And let's say the heart is pink, the outcome you're gonna get would be a pink heart, and the background is like white. But from a negative photoresist, it would basically be the background would be pink and the heart itself would be white. So then like it would be like it's just the opposite, basically.
Do you keep the pattern or do you get rid of the pattern?
So the pink one, or the one that you add, that one would be raised, and then the other one would be like kind of carved in, because you're adding something and then taking away the design instead of adding the design over top.
All right, and let's thank our artist.
Well, I know you guys were saying it was kind of unrealistic to remove the icing, but I feel like it kind of is, because I know a lot of people hate icing. So I think it might be a little bit like normal, because people do ice cakes, like they use icing to make designs. So I mean, you could theoretically have like, I don't know, like fondant underneath. So I think it could be realistic.
Thank you. All right, next up we have group 10, and again, this is the other pair of students who volunteered to draw a drawing during lunch and interpret the drawing from the experiment they learned just this morning.
Hello everyone, I'm Diego Marin from Torrance, California.
My name's Eric and I'm from Philadelphia, Pennsylvania.
Hi, I'm Avyukta Tata. I'm from Riverside and I'll be a senior.
Oh yeah, I'm also a rising senior.
I'm also a rising senior.
All right, so as mentioned before earlier today, today's experiment was on supercapacitors. And pretty much what we did today, we built our own supercapacitor, and even though we were comparing supercapacitors to capacitors and batteries, we only had the supercapacitor with us, all right? So we use activated carbon, which is kind of like powdered carbon or powdered coal, to make more room for surface area, which would be what increases surface area and allows for more room of light to be absorbed by light, or electrons in a sense, or electricity, to be absorbed by this carbon and be used for our current. In addition to this, we also use a breadboard to build our own circuit to ultimately light an LED. So there is a few differences between a supercapacitor and a capacitor and a battery. I'm just gonna, oh yeah, go for it.
I'll be explaining the difference between a supercapacitor and a regular capacitor. So capacitors are really fast, the fastest out of the three, but they store the least amount of energy at a time. So you could charge it in like a really fast period of time, but it won't store very much energy. But supercapacitors, because as he talked about, there's more surface area, it's able to store more energy than a regular capacitor. But the thing is, it has a little less power output compared to a regular capacitor. Or sorry, it has less power output. Yeah.
This image here is. Oh, are we gonna go into it?
I was going to talk, so moving on to like the difference between capacitors and batteries, the difference between them is that batteries have more power and more storage than supercapacitors or capacitors. However, they cannot give power as fast as a capacitor or supercapacitor. This is because of the chemical reactions. A battery is based on chemical reactions inside of the battery rather than the supercapacitor and capacitor, which is based on the surface area, like the activated carbon.
We're running out of time. I'll go really fast. There are 20 shelves on the top left corner of the image, and 503 books in the library. And basically, the person there is able to get books really fast, and they're able to get more books. On the bottom, there's only one shelf and less books. and they're able to get only one book, but very quickly. And on the right side, there's a computer with 10,000 results, so basically 1,000 results, the equivalent of 1,000 books. And but it takes them a week to actually collect just one book.
So each panel, each kind of division is supposed to represent either a supercapacitor, a capacitor, or a battery. This top left box is representative of a supercapacitor, and we know that because we can see that there's times 20 shelves there. And that can be representative of the active carbon, which increases the surface area, allowing for the guy to be able to move pretty fast and get 3 books. So in our experiment today, the supercapacitor was able to get or turn on the LED for a longer amount of time. And here below, we have just the regular old capacitor. And he's able to get only 1 book, right? And he only has like 1 shelf, right? So if we were to have a regular capacitor, he would be able to charge up really fast, right? The capacitor would be able to charge really fast, but it would turn on the LED light for less time than the supercapacitor were. And then all the way on the end, we have the representation of a battery, right? And this one is actually one of the hardest parts of the analogy to crack because of the fact that there are many limitations to it, which we'll get into later. But pretty much what we wanted to show, or that we interpreted, was that it takes a really long time for the battery to charge or load up the results, right? So because it takes so long, that's kind of what makes it the battery. But it gives you the most results and the most light, right, out of everything imaged here.
Okay, and moving on to limitations. So the first limitation that we noticed was that like you keep taking out books. You can't do that in a normal library because you can't just keep taking books and then the library's empty. That's not how a library works. And you have to put it back. So and then the second one is that the battery, because a regular battery actually deteriorates because of the chemical reactions, the battery over there, it's still alive. So that's the second limitation.
And yeah, the floor is now open to the audience for questions.
So you figure out that you guys use active carbon for your active materials. Why did you use active carbon for your material? And what would be the alternative if you want to reform the experiment later on? And why is the surface areas bigger than the others?
So I think activated carbon is like a nanoparticle. So the smaller the particle, the more surface area that you have. So that's probably why we have a greater surface area.
I have something else to add on. There's also other materials we could have used, like regular carbon, I believe, and another, it's like a net kind of tube. Yeah, I think graphene. But activated carbon has little grooves, and basically those grooves give it more surface area. So it's like if you went on a drive and you went straight, it'd be 5 miles. But if you took turns, then that would obviously take more time. So that's how surface area works. So the grooves give it more surface area and hence more space to hold the electrons.
I think this is actually a very nice analogy. You guys did a good job explaining it. Just one comment first. The words energy and power feel like they mean the same thing, but they don't. So energy is the amount of energy stored, and then power is the amount of energy per time.
So when you said that capacitors have higher power, you felt like that was wrong because they have lower energy, but they do have higher power because they're faster. And then the batteries actually have lower power but higher energy. So we in common language use those two terms interchangeably, but in science they have different meaning. So power is energy per time. So I just wanted to ask a question about the battery, because I actually think the computer system is a really great analogy. How can you think of the computer system as somehow being analogous to the bulk material? What is the computer system telling you about?
It's pulling information from the internet, right? So it's pulling from more sources.
But it's just pulling the information from one place. in this case, because it's just the library computer system.
Can you repeat the question, please?
So how is the computer system describing a bulk material like a battery? So what do you have to do to see the books on the shelves?
Oh,
You have to go to the library.
Go to the library and do what?
You have
to
to
search
walk
through the.
You walk up and down the shelves.
Yeah.
What does the computer system tell you about?
It's giving it all to you in one place.
It's giving you all the bulk information at one time. And so it's actually a pretty cool analogy to a bulk material as opposed to a surface material.
Oh, okay.
All right, so any comments from our artists?
We're happy that you were able to get most of it. Our initial idea actually got vetoed maybe 10, 15 minutes beforehand. So props to Daniel for drawing it really fast. But yeah, thank you.
Thank you, Group 11. Thank you, guys. All right, this is our last group, and then we have closing remarks and then food.
Hi everyone, my name is Lila Medlin. I'm from Agora and I'm a rising senior.
My name's Addison Williams. I'm from San Diego, California, and I'm a rising senior.
My name is Zhao, and I'm from Shenzhen. I'm studying in Shenzhen Senior High School. In the picture, we can see that the referee gives the baton to the runners, and the runners started to running and keep giving the baton to the runners in front of them, and the runners can win at that speed, that is 15 miles per hour, and the runners might broke their leg during the race, and they'll use a tape to fix it, and the winner can move to the next race.
Okay, so to go over a quick overview of our actual experiment, we made our own solar cells. So we took conductive glass plates, and then we smeared some TiO2 across and then heated it. And then with that square of TiO2, we dipped it in the raspberry juice, which dyed it. And then while we were doing that, we would coat the glass with graphite to act as a catalyst. And then we would drop iodine on it to replenish the lost electrons. And then we would all clip it together and then go out to the sun and use a multimeter to see its electric conductance.
So there it is. Okay. So we found a lot of analogies with this. That's the wrong way. Okay. So the first one that we found is that the referee is supposed to be representative of the sunlight because it is handing over the electron to the runner and it's starting this whole process. And then we kind of came to the conclusion that the dye is the runners just because they're bonded to the electron here, which is the baton. And that this guy is, it's also exciting the other one, which they excite the electrons as well. And we thought this might be surface area. We really weren't sure. We thought that this kind of was representative of the iodine because the electron's being handed over. We also thought that the second runner was the TiO2 because he's now bringing the electron all the way to the end. We thought the electrode was the starting line just because the electrode kind of acts as a gate for the entire thing, and the go is showing that now they're being let through. We found that this, the track was the current just because it's like a one-way path and you can see them going down it. We thought that the 15 miles per hour was the voltage because it's a very specific number and it's showing the power that not the power, and sorry, I'm very nervous right now. And then we thought that on to the next race was renewable energy because it's showing that they're coming back and it's going in like a circle. We weren't sure what this was. We honestly debated about this for a while and we still not sure. We think that this might be iodine or something replenishing the athlete.
Yeah, but a few limitations that we noticed is the fact that we were making dye sensitized solar cells. So dye is an essential part. And we didn't think that that was like shown that clearly, the role of dye latching on to the TiO2 molecules. And then also the fact that TiO2 has a very high surface area, and that's a key part of its role in holding lots of dye molecules for the more excitation of electrons. And that wasn't clearly shown as well. And then throughout, the elements and their roles seemed to like shift throughout, and it kind of like overlapped a little bit, which made it a little bit foggy for some understanding.
Floors now. Oh.
So I just want to start by saying solar cells are really complicated, and I, at the very first day, said, don't try to capture every component of an experiment. Just try to really capture a piece of it. And so there's many pieces of the solar cell functioning that are not here. So I think that this is mostly just all about the electron transfer. So you guys gave a bunch of sort of different possibilities. If you were to say, this is just about the electron transfer, how would you interpret each piece?
I would really say that this specific part is focusing on kind of like handing it over both of these. So it's kind of both like iodine and like not
so
iodine.
What's
sorry.
the electron? Maybe start with that.
We were thinking humans in general. So how or maybe the baton more
Baton.
because
I think it's the baton.
Yeah,
Because it's being
that's what's
transferred.
being passed on. Yeah.
Okay, so given that, can you just like really briefly say again, where do you think like what each person could be? Assuming that the baton is the electron. Where is the electron passed in this when the dye functions? When the solar cell functions, sorry.
It seems that the referee would be the sun then, because the electron's coming from the sunlight and being passed to the runner. That's the first step.
So the first runner would be who gets the electron first?
The glass plate? Yeah.
Well, who absorbs the sunlight?
Or the TiO2? Then,
Who absorbs the sunlight and is thus the first one to get an electron?
the dye.
The dye. So runner one would be the dye. Who does runner one give the dye, the electron to?
The TiO2.
TiO2. So runner two would be the TiO2. Who's the next person to get the electron?
Iodine.
Iodine. So whoever that other dude would be the iodine. And then what is the finish line?
My guess would be it completing, so going through the catalyst and coming back down to the original dye.
Or just the other electrode?
Yeah.
Yeah. And so, well, you're right that it doesn't capture sort of some of the energy cycling. Mm-hmm. The fact that the electron is handed off to many people is actually really well captured here.
Yeah. Any more questions? Parents, it's your last opportunity. Yeah, we are the last group.
Okay, hi, I have a question. So, I know as Dr. Sarah Tolbert mentioned that not everything is mentioned or not everything is written. My question would be, how would you represent in this analogy like the different wavelengths, right? Because a solar cell doesn't absorb all the wavelengths, only certain ones. In this case for you was which wavelength was it and how would you represent it?
My guess would be the speed of the runners, just because wavelengths, the longer they can be faster, just based off the wavelength size. So maybe the speed of different runners, just comparing that on the track. That's the only really thing I could come up with off the top of my head.
Maybe the referee could have like 5 objects.
Yeah, maybe different
different shape batons or
yeah,
something.
or different lengths of baton, and seeing how that affects the speed of the runners.
All right, let's check in with our artist.
Hi, it's me again. So I really appreciate what you said about like how I captured the electron passing. And yeah, the baton was the electron, and the referee was the sun, and the first runner is the dye.
I tried to depict the increased surface area through that little thought bubble over there, where he uses, instead of one hand, he uses two. So it's like easier for him to capture the electron. And you know, he goes through the rest of the race. And I also drew 5 runners to try to also depict like the different colored dyes and how specific light would be captured by a specific dye. So like you could specifically focus on like the first runner. But other than that, like I'm really glad that you got it, because it's a messy image and it's kind of like, I'm not a drawer, so yeah, good job. Oh yeah, I forgot to explain that. That's like unrelated, and I should not have included that. My mistake. That's basically, I'm trying to remember. It's when we put the coating over stuff, and like we had different ways of doing it, like spin coating, and I think that's what it was, and the casting. Yeah. So it's like a cast.
What specifically was this?
So,
What specifically was that?
Oh, I messed up and I scribbled it out. But yeah, I tried to depict that it was like being casted. That's just a mistake I made. So yeah, that's it. Great.
Thank you. Sorry. Okay, so we're going to go to some closing remarks. So hopefully you saw that your students learned a lot of stuff this week. It was jam-packed. So we're really proud of them. I hope you guys are really proud of them. And most importantly, I hope you all are very proud of yourselves. Okay, it's got to come internally. Can't just seek all these external sources of validation. We need to be proud of ourselves. Okay? And I also just want to extend a thank you to all of our parents. So thank you, parents. I don't know if the students know, but this is a pretty expensive program. So your parents are really, truly investing in your education. And I hope you all took advantage of this opportunity that you had this week. And again, we really thank you, parents, for supporting your students in seeking these opportunities. Because you don't know what you want to do until you try some stuff. So we might not, all of them might not go on to be scientists, but hopefully they learned. Maybe they learned that they don't like science. That's okay. So again, it's all about learning. And so then a message to our students. You are our students for 5 days, but you are our students forever. And we want you to succeed, okay? So we want you to stay in touch with us. We want to know what it is you're pursuing beyond here, if it's college or university, a PhD, an MD, starting a business. And then I wanted to alert you to some of our other opportunities that we have. So again, we have this CNSI Nanovation competition, that's nanoscience and entrepreneurship. You form a little team, you propose a product using nanoscience, and that process happens in December and January. And then we have other CNSI summer sessions courses offered through UCLA summer sessions. You guys are here in Nanoscience Lab. These are some of our later sessions, but we also have nanoscale microscopy, where students really use the instruments in our tech centers. And then Applications of Nanoscience is a 2-week summer program where they basically do that nanovation competition in 2 weeks. And then lastly, we write letters of recommendation. So you just shoot me an email, I'll send you a little form to fill out, and we will write very personal and strong letters of recommendation for you guys. So just to let you know, the UC system does not accept letters of recommendation. So I cannot write you a letter to get you into UCLA. That is not how it works. But we do write letters of recommendation for other universities, other summer programs, other opportunities that you guys want to pursue. So anytime from here on out, even if it's a year from now or 2 years from now, you just shoot us an email and we will write you a letter of recommendation. Okay? And then lastly, we talked about our skills in life. One of them is reflection and introspection. So I'd like you all to take a moment to think about what did you know about science or nanoscience before you started this course? What did you learn over the last week about science, research, science communication, teamwork, and about yourselves? Okay, and then I'm going to pass it off to Professor Tolbert for some closing remarks.
Okay, so I just want to take a quick second to again thank some people. I want us to all thank the graduate students and undergraduate mentors who were a huge part of this program. For any of you who are here, can you just stand up and can we please have a round of applause for all of our mentors who were just such a giant part of making this program work. I just want to say, Shailene mentioned something about, nothing is cheap anymore. If we did not have such a dedicated set of people who are helping us, I can tell you that to have this sort of level of instruction would have been astronomically more. And so the fact that you guys are teaching and learning as part of your degree programs is also a huge advantage to all of these people. We need to thank Shailene and Rita, who have been the people on the ground every day, making sure that everything happens. So a huge round of applause for your lead instructor.
Want to thank parents. I've been you on this side. My kids actually took these classes. They had to pretend they didn't know me, but they still liked the classes, even if they were embarrassed that they knew me. I can tell you from both sides that it's a really great learning opportunity. And then I just want to give you some perspective. So at the very beginning of this week, I said, okay, we're going to make you draw pictures, and you're going to roll your eyes at me and say, I'm too old to draw pictures. But I hope that you have learned in this process that communicating science is really hard. And in our current society, there are people who understand science, people who appreciate science, people who are afraid of science, people who think that science is evil. And the only way we're going to bridge the gap between all those different people is if we learn to communicate concepts in a way that is simple and clear. And so I hope that this is your first step in a process, not only of understanding and exploring whatever topics make you super excited, but that realizing that you have to be able to communicate the essence of those concepts to people who know nothing about them. And that only in that way can you make a real impact on the world. So I hope this was the first step in that journey. And I hope you had a lot of fun in the process, made some friends, and want to thank everybody for participating. And now finally, we get to go have a reception.
Okay, just some little mini announcements. We are always looking to improve this course, so if our students could please whip out your phones, scan my QR code, and take our survey, we would really appreciate your feedback. A second announcement is that if you are living in the dorms and you are leaving tonight, please send a text to your RA so they know not to look for you at curfew, or else they're going to blow up your phone tonight. Okay? And then the last thing is that we would like to take a class photo. And so we're going to go outside in front of the building under the California Nanosystems Institute logo and take a class photo before we go get food. Parents, you are welcome to get food first. All right? All right. Thank you all.